The World Trade Center in New York City. Over 60,000 people work here, and another 90,000 visit for business and pleasure every day. More than 1,200 businesses and governmental agencies from over 60 countries involved in marketing, finance, insurance, transport, and international trade are brought together in this complex. At the heart of the World Trade Center are the two 110-story skyscrapers rising about 1,400 feet into the sky, the world's second tallest buildings. Every floor of these towers is approximately 1 acre in size, with no internal columns to assure maximum flexibility in layout. That's a total of about 200 acres of precious space in the two towers alone. Over 1,300 feet in the air in one of the towers is a ballroom which can accommodate up to 1,000 people. Each tower is serviced by 100 passenger elevators, including express elevators which can carry up to 55 people at a high speed. The World Trade Center is a city in itself. It has the electric consumption of about 50,000 homes. The tower's cooling systems alone draw nearly 87,000 gallons of water every minute from the neighboring Hudson River. What's holding this fascinating and enormous city literally up in the air? Structural steel, over 200,000 tons of it. We may not realize it, but steel plays a very important role in our everyday lives. It's not only used in the construction of our high-rises and other buildings, but in bridges that span our rivers and the millions of cars that cross them each day. In millions of miles of pipes that carry the fuel for those cars around the world. In our monuments. In our refrigerators, washing machines, tools, and watches. And in sports complexes that contain the energy and action of thousands of fans as they enjoy a Saturday afternoon game.
Hello, I'm Patty Satalia, your host for this program. Every year, millions of tons of steel are produced around the world. A good portion of this amount is made in the form of structural steel. We depend on steel's strength, durability, and flexibility. But do we know about making steel and putting it together? In this program, we'll see how steel is made, readied for construction, and finally put together in the form of a structure. These three processes are commonly referred to as production, fabrication, and erection of structural steel. Since its inception and first use in 1885, production of structural steel, which is also known as structural shapes, has gone through many developments. However, one thing remains unchanged. Its main ingredients are iron ore, coal, and limestone. But how do these rocks become this piece of steel? Production of structural steel may be divided into three stages: make iron, make steel, and shape steel.
To make iron, iron ore is mined and crushed to separate the iron-bearing particles. They're rolled and baked into pellets for shipping. Limestone and coal are also mined and transferred to the steelmaking plant. The coal has to be changed into coke, which burns cleaner and with higher intensity than coal. Coal is preheated and fed through pipelines into coking ovens, where volatile materials are driven off. The coke, now almost pure carbon, is then cooled with water and fed onto conveyor belts, while iron ore and limestone are transferred from the stockpile to a bin. Operators carefully add a charge of coke, iron ore, and limestone to the blast furnace, so called because of the continuous blast of hot air it receives. This air causes the coke to burn so hot that it reduces the iron oxide in the ore to pure iron, taking away the oxides as carbon dioxide. The limestone combines with the impurities from the iron ore, forming slag. The slag floats to the top as a cindery layer, leaving the heavier molten iron at the bottom. There's a notch in the furnace for drawing off the slag and a lower hole for tapping the molten iron. Product evaluation is a continuous process as quality control personnel monitor every phase of iron and steel production. From the furnace, the molten iron flows into cars with brick-lined interiors. Like giant thermos bottles, they will keep the metal hot while it's being transported to the next location. Now we're ready to convert the iron to steel.
Steel is an alloy that contains iron as its major component and small amounts of carbon as the major alloying element. Different amounts of other elements such as manganese, silicon, chromium, and nickel may be added to make a variety of steels with different characteristics and properties.
The primary materials for steel making are the molten iron and scrap. Iron and steel in the form of scrap can be recycled over and over. It's a practical way of conserving our resources of raw materials.
In fact, blast furnace iron provides only about half of the metallic raw material for the steel industry. The other half is obtained from scrap produced in subsequent manufacturing operations and from obsolete steel products.
There are two ways of making steel. The electric furnace utilizes scrap steel. This type of furnace is a viable option in areas where handling facilities for raw materials are limited, but scrap is available. To melt the scrap quickly, electrodes are lowered into the furnace. Electric current arcs from one electrode to another through the metal scrap and melts it down, producing new steel. However, the principal method for producing steel is by using the basic oxygen furnaces. These modern furnaces, called BOFs, can turn a charge of scrap and molten iron into over 250 tons of steel in just over 30 minutes. The BOF tilts to receive its charge of selected scrap. It rotates to distribute the scrap over the furnace bottom, then tilts again to receive its charge of molten iron. Then an oxygen lance is lowered. As the lance tip is water-cooled, oxygen is blown across the metal at supersonic speed, creating intense heat, about 3,000 degrees Fahrenheit, as it reacts with the molten iron. The oxygen combines with carbon and other unwanted elements from the mix, and steel is produced. Alloys are added to create different types of steel with the desired strength and properties. Aided by computers, the steelmakers monitor all the variables that influence the quality of the steel. Many steel-producing mills are very sophisticated plants equipped with state-of-the-art mainframe computers and control systems. During the steelmaking process, samples are taken for testing. If metallurgical tests are satisfactory, the furnace is tapped. The refined steel pours from the furnace through a tap hole located below the layer of slag. The end result is a ladle of molten steel made to the customer's exact specifications and ready for shaping. This steel will then go through continuous casters to make slabs, billets, or blooms. In the continuous caster, the steel flows through nozzles into water-cooled, down-curving molds. Sufficient skin forms to enable the steel to solidify gradually as it travels downward. The steel emerges from the curving mold as a continuous rectangular ribbon. The steel then goes through a straightener and is either sheared or torch cut to the desired length. This process, like many others, may be controlled by computer-operated equipment. Slabs and billets are used to make steel plates, pipes, rods, and similar products. To make structural shapes, blooms are heat-treated and then transferred to another mill where they will be made into different shapes. Here, the bloom goes through profiled rollers repeatedly to make the desired shapes. Today, structural steel is produced in literally hundreds of shapes and sizes, and in a variety of steels with different strengths. The rocks we saw earlier have now become a very long piece of structural steel. This piece will be cut to a number of lengths and allowed to cool before each piece is marked, identifying its size, steel type, and production mill. Now the stock is ready for shipping. Who knows, maybe the piece we just saw is now supporting the roof over your head or the deck of the bridge you drive over to go home.
So far, we've briefly gone over the processes involved in the production of steel. Next, we'll take a look at fabrication of structural steel. After the steel is produced, it will be transported to the fabrication shop, where it will be cut, punched, and pre-assembled as much as possible, according to the engineering drawings and specifications. Generally, it's desirable to do as much of the assembly in the shop as possible. However, problems such as transporting and erecting very large assemblies limit this possibility. Now, before we talk more about fabrication, let's see how steel members are connected to each other to make a structure.
This is one way a beam may be connected to a supporting column. Here's an exploded view of the same joint. To complete this connection, it is necessary to make holes in the beam and column, to cut and drill holes in the two pieces of angles, and then to bolt them all together. Later in the program, we'll see how this is done. Here's a beam girder connection. Note how the top flanges of the beam should be cut or coped at the ends to provide a level surface to support the floor deck. To make this connection, the top flange of the beam at the end has to be cut or coped. Further, connection angles should be made. Holes should be drilled in the beam and girder, and the part should be bolted together. This is an example of a less common column-to-column connection. To make this connection, the thick plate is welded to the bottom column and the angles are welded to the plate. This is done in the fabrication shop. Then at the construction site, the top column is bolted to the angles and welded to the plate.
These are only a few examples of what it takes to join steel members. The steel fabricator plays an important role in all of these processes. But what else does a fabricator do?
We get a set of architectural, a set of structural drawings, and at that point we turn it over to the drafting room to generate details. The drafting room makes erection drawings, they send them out for approval to the engineers, they come back. They're either approved or not approved. We move forward at that point and put the details into our CAD system. We generate the details. We send the details out for approval. And when they're approved, we make our cutting lists, we make up our disc, and prepare the job for the shop. It goes into the shop, goes through our system, from sawing it to the final fabrication and painting if necessary, gets stored in our yard for a delivery to the job site, which is in probably a time period of 10 to 12 weeks.
Let's take a closer look at some of these processes.
The operators in the CAD room enter the necessary information from the engineering drawings into the computer. The computer generates pictures of the members and details of the connections. This information is then printed and plotted and sent to the engineer for inspection and approval. Once the engineer approves the drawings, computer discs are generated and sent to the shop. The discs contain information that enable the computer-driven machines in the shop to do the necessary work, such as cutting and drilling of steel members. Fabrication shops are very busy and sometimes very noisy places. Lots of activities go on in the shop. Typically, the first step is to cut the members to length. Stalks of steel enter the cutting machine by conveyors. The operator inputs the size and the desired length of the member. An automatic arm will be lowered, stopping the stalk at the appropriate point as it goes through the saw machine. Then the blade will come down and cut the steel. The piece will then be labeled and rolled out. From the cutting area, the member will travel on conveyors to the next station, where holes will be drilled for making the necessary bolted connections. The machine operator inserts the disc prepared earlier into the computer as the member is fed through the drilling machine. By pushing a few buttons, the operator initiates the process. From here, the computer takes over, and the operator goes on to roll the next member into position. The steel will automatically go through the machine while its location is monitored by measuring devices using laser and other technologies, stopping at the appropriate points for holes to be drilled. Depending on the size and type of connection to be made, a number of holes may be drilled in the web and/or the flanges of beams and columns. This is a column with beams connected to its web and flanges. Here's another such column, but note how the column size changes a few feet above the floor, not at the floor level where the beams are connected. This avoids congested connections. All the holes will be drilled in one pass as the column goes through the machine. On a small monitor, the operator is able to look at different views of the member in the machine, indicating the number, location, and size of holes needed. He can also note the precise location of the drill bit in the X, Y, and Z directions. Once all the holes are made, the member will travel on conveyors to the next station, which may be the coping machine. The coping machine burns steel to cut members to length, like a saw, notch, and make holes of different sizes and geometry for mechanical equipment. However, this machine is used mostly for coping beams. Let us see how this is done. Here again, all the operator has to do is insert the proper disc in the computer and initiate the process. The piece will automatically go through the machine, stopping at the appropriate locations for the burning operation to proceed. Normally, the edges that are flame cut by this machine are very smooth and do not require any additional work. From here, the member goes to the layout station where angles, plates, and other connection parts are bolted or tack welded. In the past, mostly rivets were used to join pieces of steel. This was an expensive and dangerous process, as a crew of 4 had to work with fire, very hot rivets, and noisy equipment to drive rivets. Today, high-strength bolts and welds have made joining steel members faster, easier, more economical, and more reliable than ever before. There are also new products that may be used in steel fabrication. One such product is the tension control bolt. Note the splined end of the bolts. Here's how it works. The wrench holds both the nut and the splined body of the bolt and turns them against one another to tighten the bolt. When the required torque is achieved, the splined end twists off in the wrench. A plunger inside the wrench discharges the splined end. Let's see how this is actually done. Pay particular attention to how long it takes the worker to install and tighten a number of bolts. And here are the ends sheared off. From here, the piece will be taken to the welding area and welded if necessary. This includes welding of pieces such as base plates or stiffeners and connection fittings. Welding, too, may be performed using automated machines, producing very efficient, economical, and reliable results. Incidentally, the introduction of large steel shapes has drastically reduced the need to rivet, bolt, or weld numerous pieces and shapes. For some steel members, this may be the last stop in the shop, but there are many other areas in the fabrication shop where pieces needed for joining steel members are produced. Angles are cut and punched for a variety of connections, some of which we have already seen. Stocks of angles are automatically delivered to an angle machine, which will cut them to the desired length and punch holes in one or both legs at the appropriate locations, all in one pass. The cut pieces are then led to another automatic conveyor, which will deliver them to the right receptacle. This process, too, may be fully automated and computer controlled. Another operation usually performed in the fabrication shop is torch cutting of plates for different purposes. Some of today's equipment can very accurately cut plates with a variety of thicknesses. This is done by computer-operated machines which receive the necessary cutting information from either a computer disk or by tracing a template of almost any shape or geometry. Some of these machines are capable of producing several pieces in one run, with edges that do not require any further finishing. There are a number of other operations that take place in the fabrication shop. They include shearing plates, punching holes in small plates, and bending of steel members. The last process that a steel member may go through in the shop is painting. Specifications may require certain pieces to be cleaned and painted before erection. This requirement depends on the type of steel and the environment in which it is to be used. Once a piece has been through all of the necessary operations in the fabrication shop, it is taken to the yard, loaded onto a truck, and transported to the job site or storage yard. Frequently, these pieces will have to be assembled under difficult conditions where it's not easy to maneuver them to align the holes and make members fit. This is why precision in fabrication is crucial.
The process of delivering, hoisting, and placing steel is often a very critical one, which has to be carefully planned and orchestrated. Sometimes there's not enough space on the job site to store all of the fabricated steel. Therefore, the pieces have to be delivered from the fabrication facility or the storage yard in the order in which they will be erected.
That brings us to the next stage, the erection of structural steel. Erection of steel is the assembling of the fabricated steel to make the structure. Typically, this is done by lifting and placing the steel members in their appropriate position, and then temporarily fastening them with a few bolts or welds. At this point, the structure is capable of supporting its own weight only and cannot resist lateral loads. Therefore, it must be temporarily braced so that it will not fall over during construction. Columns and beams on the perimeter of the structure are erected first. When a worker receives a member for erection, he lines up holes by running a rod through them. Then he puts in a few bolts and temporarily tightens them with his wrench. During this process, the crane operator plays a very important role. He has to deliver the steel to the exact location, often without being able to see it. He receives instructions from the iron workers through hand signals or radio. Because of the sensitivity of their work, crane operators change shifts frequently to avoid fatigue.
Despite all of the care taken to make sure that everything is fabricated and assembled as planned, it doesn't always work that way. Occasionally, minor misalignments and errors just will not let members fit.
Sometimes they are forced to fit, which could create assembly or built-in stresses. However, in some cases, more drastic actions may be necessary. On the day of our visit, this member just would not fit. It took workers much longer than usual to torch cut a connected piece and weld it back after erecting the beam. Once a section of the structure is assembled in this manner, workers come back and permanently fasten the members with additional bolts and welds. The special wrench these workers are using will automatically stop once the required torque is achieved.
Quality control is very important at this stage. To ensure that the bolts and welds used are sufficiently strong, a certain percentage of them will have to be inspected.
Of course, each job has different specs. This job was spec'd at 50% of the semi-penetration welds had to be inspected. 10% of each bolted connection has to be tested, and 100% of the full penetration welds must be tested.
Erection of structural steel has always been and always will be very challenging. Many times workers have to assemble very heavy pieces at high altitudes while several pounds of equipment and supplies hang from them.
This may require walking on members hundreds of feet up in the air or climbing up and down columns, such as we see in these shots of the construction of the Empire State Building about 60 years ago. Workers are not only concerned about their own safety, but also that of others as well. Often there are other workers, cars, and pedestrians below them. It should be emphasized that today's skilled workers and job safety requirements have made erection of structural steel very safe for the workers and others around them. However, the challenges of erecting steel structures are not limited to safety issues only. Sometimes special conditions are encountered in the erection of steel structures, which call for new and innovative techniques.
For example, in very tall structures, it's impossible to find cranes that can reach the top of the structure from the ground. In such cases, self-lifting cranes may be used so they can lift themselves as the construction proceeds. In the case of the CN Tower in Toronto, Canada, the tallest freestanding structure in the world, a mast had to be put in place over 1,500 feet in the air. The problem was lifting and erecting heavy steel structures accurately and safely at a high altitude in Toronto's cold winter. The solution? A helicopter. Once pieces of the structure were pre-assembled and after several practices on the ground, a special helicopter was used to lift and assemble the mast. This idea saved over 6 months of construction time. In some cases where the conditions don't allow much room for maneuvering, such as the construction of the frame for the revolving restaurant at the top of the Space Needle in Seattle, the structure may actually be assembled on the ground once to make sure everything fits before it's lifted and permanently assembled.
So far we have seen how structural steel is produced, fabricated, and erected. What's your role in all of this? What contributions can you, the engineer, make in the construction of a steel structure? Although much of the design and fabrication of the structural steel may be performed by computer-controlled equipment, everyone involved in the process, including the engineer, has a very important role. We should not lose sight of the fact that computers do what we program them to do.
Computers can make our life very complex in terms of the design of the structure, but that may cause us to lose the benefits that we're looking for when we go into fabrication and erection. And those qualities that we're looking for are repetition and regularity, because once we have those, we begin to cut down on the cost of the fabrication and cut down on the cost of the erection.
Professional judgment and common sense should be used by everyone in accepting the outcome. While automation could make things easier, it could also produce results which are not practical and economical, among other things.
Before, when you would have base plates on a job, a good-sized job, for instance, the base plates, if they were two different sizes, you would put an 1.5-inch base plate and an 1-inch base plate on, and that would cover 200 columns. Now every base plate that comes out of a computer is broken down into 1/8 and 1/4 of an inch. So now consequently you've got maybe 35, 40 base plate details to do. And we're saying that's more expensive than if you just added that little bit of plate and covered all the base plates under 2 or 3 different sizes. It makes more work in the drafting room. It's more work to go out and buy these different kinds of plates, different sizes, and it makes a lot more work out in the shop to pick out all the different thicknesses of base plates.
The structural engineer should be to some extent familiar with the capabilities of the equipment used and the procedures involved in fabrication and erection of structural steel. Sometimes minor changes in the design can lead to significant savings. Some designs may not be very practical to fabricate or erect. Although we wish to select the lightest possible shape, selection of a smaller or lighter member will not necessarily result in more economy. For example, choosing a slightly larger beam or column size, if possible, may make fabrication and erection as a whole more economical, despite a larger initial cost per member.
The component of the structural steel versus fabrication and erection in the 3 components that make up a structural steel frame. The structural steel has actually decreased in the last 20 years from maybe 50% of the value of the steel frame up and in the air to now 30%. Consequently, if we spend a little bit more on the steel and make some savings in the erection and the fabrication, it's probably money very well spent.
So I guess what we're really saying to the structural engineers of the future is let's not make it so technical. It can be simplified and left simplified. We're simply trying to design steel for buildings and not really trying to put clocks together. And it can all be done very well by really staying with the basics of structural engineering, and that's designing a beam or a column that fits that spot, but using it in other spots also. It makes the economic part of the steel go much, much better.
The engineer should be thoroughly familiar with industry standards and what can be done and what can't be done in a reasonable fashion. We don't want him bringing to the specification tolerances that are difficult to live with. We do want him to understand things like camber and its uses and how it can help us. And we do want him to understand the tolerances relative to other systems in the building, like the wall system, the curtain wall. How does that relate to the structural steel frame? How does the deck system relate to the structural steel frame, and how is it used? So if he can handle these things, this repetition, this regularity, if he can understand that the mill steel is not something to necessarily be saved trying to come in with the lightest weight structure, and if he can understand how the building goes together in tolerances and the likes, it's a long way to producing a cost-effective structural steel frame.
Remember, what you as the engineer want done should be doable with reasonable effort and facilities if it is to be a practical and economical design. For example, are bolted or welded connections arranged so that steel may be field assembled with ease? You, the engineer, are and always will be a very important part of the construction industry. So be practical, explore alternatives, be innovative, and join the thousands of engineers who practice good engineering for you and me every day.